MAVEN is the next Mars mission that is going to be launched. It's the one that was selected for launch after the Mars Science Laboratory, which will be launched in about 2 years. We launched in 2013. What I want to do tonight is tell you a little bit about the mission and what we're going to do, and talk about what the science drivers are to tell you why this mission is what it is. If I told you that it was an aeronomy mission, 2/3 of the people in the room would fall asleep instantly. The A word does that to people, so I'm going to tell you instead why it's an astrobiology mission, why this is relevant to the search for life elsewhere. I want to start with what I think is the overriding question about Mars. Did Mars ever have life? And you can see this is how I'm going to tie it back. I show pictures of a rock to make it interesting to people, and then I'm going to segue into the upper atmosphere. Based on our understanding of life on Earth, we think that there are relatively simple requirements that would be placed on an environment in order to be able to support life. Liquid water, access to all the elements, and some source of energy. You need liquid water as a medium in which life exists, something that nutrients can diffuse in toward an organism, waste products can diffuse out. I'm not going to get into the argument of does it have to be liquid water, because as you'll see, I think liquid water is the most likely thing we're going to find on Mars. We could argue about liquid nitrogen and methane and ethane when we talk about Titan. That's not tonight's talk. We need all of the elements out of which you would build life. Carbon, hydrogen, oxygen, nitrogen, things like that. Another 24 or so less abundant elements, but elements that contribute to the chemical complexity that lets molecules combine in very interesting ways that have interesting chemical properties that look a lot like life. And you need some source of energy. On Earth, if we think about the source of energy, most of the life on Earth is driven by sunlight through photosynthesis. Plants take sunlight, it triggers chemical reactions in the plants that make energy available. We don't photosynthesize, although I think that would be sort of cool if we could go out and lie on the beach and get energy instead of have it sapped from you. But we eat plants that do photosynthesize, or we eat cows that eat plants that photosynthesize. That's most of the energy, but there's a small amount of energy that comes from other sources, and I want to focus on that, and that's chemical energy that comes from reactions between water and rock. Water and rock on Earth are very abundant in our environment, and reactions go forward naturally, which means they give off energy. And if organisms can somehow stick their fingers, so to speak, into that reaction, they can take advantage of it and utilize some of that energy. We think that that was the source of energy that was the first source of energy for life on Earth. And if we're looking for life on Mars, we think that could be an important source of energy, especially early on. Liquid water used to exist on Mars, but that it can't exist today. Mars is way too cold, way too dry an environment. These pictures down at the bottom are meant to remind me that these second two bullets are relatively easy to met. This is one of the meteorites that has come from Mars. This is Alan Hill's meteorite, ALH 84001. It's a name that just rolls off the tongue after a while. This was the one that a decade ago, if you guys remember, was the trigger for a lot of discussion about whether there could be life on Mars. It's one of about 36 meteorites that have come from Mars and have been collected here on Earth. This one was collected in Antarctica. You go out onto the ice sheets, and if there's a rock, it fell from the sky, and they go out and pick up the meteorites. I have one that fell in Nigeria about 45 years ago, and I think it's really cool to own a piece of Mars. I'm absolutely convinced this is a piece of Mars that was knocked off of the surface by an asteroid. It floated around through the solar system and crashed here on Earth. What's interesting as an aside, when I became convinced that these meteorites were from Mars, I had to have one. And so I went and found a meteorite dealer and bought a piece of it. This piece is about 1.5 grams. They're expensive because they're rare. And when I bought it, the going rate for this was about $100 a gram. And I figured that's a lot more interesting to own one of these than what some of the students at CU would spend $100 a gram for. And after all the brouhaha about possible life on Mars, the going rate shot up. It became $1,000 a gram. And I gave serious thought to selling this rock, taking the $15,000 and buying a boat. I'm sorry, I misspoke. It jumped up to $10,000 a gram. So I could have gotten $15,000 for this. I should have done that because the price, of course, dropped like everything else. This rock tells us that, and the other Martian meteorites tell us that Mars has all of the different elements that we would expect to find on a rocky planet, and in fact, all the elements that we need to be able to support the chemical processes that create living organisms. More importantly, that rock has evidence that water flowed through it. That's very common on Earth, where water will flow through the pore spaces in rock and leave behind chemical remnants, chemical traces of that. And it was within one of those that they found things that they thought looked like fossilized microbes. Turned out to be not credible evidence. It took 5 years to discover that. It was contamination from falling on the ice in Antarctica and from how they processed it in the lab. But nonetheless, it says that Mars, at least on the face of it, appears to meet the requirements to support life. So I want to talk about some of these requirements a little bit. Water in particular is the most difficult. We have a lot of evidence for water ice on Mars. You see it all over the place. You find it in the polar caps. The North Polar Cap is made of water ice. We know that because we can look at reflected sunlight that has the spectral signature of water ice. On Earth, water ice marks the polar caps. And the way I look at this white stuff outside, it's really just the most equatorward extension we're going to see of the seasonal polar cap here on Earth. Those are words we use to describe what happens on Mars. The Phoenix mission, about a year ago, directly sampled the ice. It landed at the high latitudes just off of the North Polar Cap and found water ice buried about 4 or 5 inches under the surface. And then most recently, the Mars Reconnaissance Orbiter spacecraft looked at recent impact craters. By recent, I mean things that happened within the last year, or 2 years, or 6 months. They had pictures that showed nothing and then pictures showing an impact crater. It must have happened. And they found white stuff that had been knocked out from it that is water ice. The problem is there's a lot of evidence for water ice, but water ice isn't terribly useful to microbes. You need liquid, and although there are ways that organisms can get liquid out of ice, the temperatures are generally too cold to allow that. We want to look for liquid water. One of the pieces of evidence, we don't see liquid water, but we look for circumstantial evidence that it's been there. If you look at the ancient surfaces, and we know this is an old surface because of all the impact craters on it, you have a surface and it just sits there for a few billion years, things fall out of the sky and hit it and create impact craters. We see things like this branching system of what look like river tributary valleys. This is called a valley network. Geologists have very unimaginative minds. It's a network of valleys, so they call it a valley network. But morphologically, the appearance is one of runoff of liquid water. These occur only on the ancient surfaces, older than about 3.7 billion years old. These things formed early in Mars history and then stopped about 3.5 billion years ago. They look like they were formed by liquid water flowing over the surface. And in fact, I have a very, what I would consider to be a subtle geological argument, but very convincing, that argues that these were formed by liquid water and not by something like liquid CO2 or liquid sulfur dioxide or the wind. So let me go through this argument. It's very subtle, so follow along. When you look at these, they look like they were carved by water. Did I go by too fast? I can say it again. This is how geology works in the planetary environment. You see things and you ask, what does it look like here on Earth? Is that what it could be? What makes sense? And these things look like they were carved by liquid water. There are other features. I should tell you, these things, this is about 5 or 10 kilometers across there. There are other features that look like they were formed by water. We're looking now at a scene also of the ancient heavily cratered terrain on Mars, this one about 1,000 kilometers across. And we see impact craters like this one that are very heavily degraded. This one is a nice, crisp, fresh one. It looks like it could have formed almost yesterday. But this one has been eroded. That fresh raised rim has been degraded away. There's a scalloped edge on the interior that looks like the spur and gully topography you might see on a scarp here on Earth or on an impact crater here on Earth. And it looks like this has been very heavily eroded. Again, everything older than about 3.5 billion years in age has been very heavily eroded. The younger ones haven't. What this tells us is that whatever is going on relative to water happened early on in Martian history. There was evidence for a lot of water at the surface early and none today. We see chemical evidence that tells us about liquid water. We're looking here at a map of the planet where the colors represent places where the Mars Express European Space Agency mission identified clay minerals and hydrated minerals, minerals containing water. That chemical alteration that creates those minerals happens only in a wet environment. So again, we see evidence for liquid water. The occurrence of liquid water is the puzzle, because Mars is half again farther from the sun than the Earth is today, so it doesn't get as much sunlight. It has a much thinner atmosphere than the Earth does, so it doesn't get very much greenhouse warming. And temperatures today are really cold. The average temperature at the surface is about, let's see if I can do the math, about 90 degrees Fahrenheit below zero. If you think in terms of centigrade, it's about minus 50 degrees C. That's the average temperature. That's way too cold for water to exist in liquid state. There's other evidence for water. I was about to go on, but I forgot about this one. If you remember the Mars exploration rovers, Spirit and Opportunity, Opportunity found evidence for liquid water. They see it in the layering inside one of the craters they looked at. The most interesting were these features that they dubbed blueberries, that are little round spherical things about the size of a blueberry or a pea that have been eroded out of the rock. These are concretions formed by minerals that dissolve in water as the water flows through the rock and that get deposited somewhere else. They're really common here on Earth. And finding them on Mars says without any doubt there was liquid water. They found what's termed festoon cross-lamination, where the layers in the rock take on this sort of consecutive U-shape appearance. That forms when sediment gets deposited in very shallow liquid water, in running liquid water environments. Now, I know that this is convincing evidence for liquid water for two reasons. The first is all my geologist friends tell me this, and I believe them. But the second is, and you guys may remember this, when the Mars rovers landed, God, what was it, 4.5, almost 5 years ago now? Their goal was to find evidence for liquid water. And Long John Silver, the fast food seafood chain, came out with an ad that said, if they find liquid water, if NASA certifies there was liquid water, they would give away free shrimp to everyone in the country. And after the first press conference where Steve Squires and the Opportunity team described this evidence, Long John Silver's gave away free shrimp to everyone in the country. They had a day where all you had to do was walk in and get it. I know they're not going to do that unless they were really convinced. So I now take it as a given that there was evidence for liquid water, that the evidence is pretty convincing. So we have this puzzle. And don't worry, I'm going to get to the MAVEN mission. I'm almost there, because this puzzle is really the heart of it. Mars was warmer back then because it must have been warmer to have had liquid water, because it's too cold for liquid water today. The valley networks really look like they were carved by water that was stable, flowing over the surface. How do you do that? How do you get warmer temperatures to allow liquid water? And the problem is worse than that. Remember, Mars was further away from the sun. It's got a thin atmosphere. The problem is worse because 4 billion years ago, the sun was 30% dimmer than it is today. That means you needed to raise the temperature even more to get up to liquid water temperatures. The obvious answer, it's up here, it's a greenhouse atmosphere. You have a gas like CO2 filling the atmosphere. The CO2 lets the sunlight in, it doesn't let the heat out, and the temperature goes up. We're actually doing this experiment here on Earth today by increasing the amount of CO2 in the atmosphere and seeing what the temperature response is. And I have to admit, it's incredibly scientifically far-sighted for everybody on Earth to get together and do this experiment just to see what the explanation is for Mars liquid water. Oh, come on, how about at least a kitty laugh? Thank you. The best explanation is a greenhouse atmosphere. We think that you're going to get disagreement. In fact, those of you who were here for Brian Toon's talk, when was that, about 2-3 months ago, would have heard the opposite side of the story where he doesn't think a greenhouse atmosphere did it. I think it's pretty convincing that that's the best explanation and really the only viable explanation. You need about 10 bars of CO2. 1 bar is the amount of atmosphere we have here in the Earth's atmosphere today, the air pressure. So you need about 10 times this much CO2. That's not an unreasonable amount. Earth has that much CO2. Most of it just happens to be locked up in carbonate minerals, minerals that have CO2 bound into them. Things like the white cliffs of Dover, the rocks of Gibraltar, these are all carbonate minerals. On Mars, if we had that much CO2, where did it go? The quick answer is carbonate minerals, but we don't see any evidence for carbon-bearing, CO2-bearing minerals in the abundance that would be necessary to explain a thick early atmosphere. In fact, Mars geologists for 30 years have been looking for where's all the CO2, and they've been saying, we don't understand this because we can't find it. The answer is it's lost to space. It didn't go down, it went up. And now finally, we're going to get to the MAVEN mission because that's really the thrust of it, to understand how gas was lost from the atmosphere to space. We have evidence that the atmosphere had been thicker in the past, this greenhouse concept. There's a lot of evidence that gas has been lost to space. And I want to mention just a couple of the pieces of evidence really quickly. The first listed up here is isotopic fractionation. And let me give you an example. Hydrogen is one of the atoms that makes up water, H2O. Hydrogen exists in a heavier form called deuterium. The hydrogen atom is just a proton, the nucleus. The deuterium atom is a proton and a neutron, so it's heavier. If escape to space is occurring, the hydrogen is lighter than the deuterium. It should escape more readily. The stuff left behind should become enriched in deuterium relative to hydrogen. You find that out by measuring this ratio of D to H, deuterium to hydrogen. And on Mars, what you find is that ratio is 5 times what it is here on Earth. And that sort of variation can be explained only by loss of a large fraction, something like 90% of the hydrogen, to space. We see this consistently across other isotopic systems, other atoms. Argon, carbon, nitrogen in particular, all of these, the heavier version of the atom is more abundant than the lighter version and suggests we've lost a very large fraction of the gas to space. We've detected gas being lost today. We have spacecraft in orbit. Actually, the Russians and Europeans have done this much more than we have. they've been trying to measure the gases that are being lost, and they haven't measured all of them, but they've measured some of them. The loss rates are small today, but it demonstrates the gas is being lost. And I think I'm not going to go into this last one because it would take me more time than I think we have tonight to go into it. The bottom line then, in terms of the scientific driver behind the MAVEN mission, where did the CO2 go? Could it have been lost to space? How would it be lost to space? Ultimately, only if we understand the role that escape to space has played in changing the Mars climate will we understand the history of the Mars climate, the nature of habitability, and the history of Martian habitability. Let me say that differently, that CO2, water, nitrogen, these are gases that we expect to find in an atmosphere. And when there's a lot of it, and liquid water is stable, organisms would love to live there. They would be quite happy. If you take the gas away, the temperature drops because you've lost that greenhouse warming, and you've made the planet not habitable by microbes. Only if we understand the role that lost to space has played are we going to understand this history of habitability. So the scenario that we're exploring, if you think of it in these terms, early on, Mars had a magnetic field, much as the Earth does today. We have evidence because we can measure remnant magnetization on the planet, places that hold a memory of when Mars was magnetized. And that magnetic field keeps the solar wind from hitting the planet. That happens today. It protects us from the solar wind, and it would have protected Mars. About somewhere between 3.5 and 4 billion years ago, we think that magnetic field shut off. The solar wind would be able then to impinge directly onto the planet, and it would start to strip away the gas. Very quickly, in a matter of only a few hundred million or 500 million years, we think the gas was lost and left us with this cold, dry planet we see today. What we want to do with the MAVEN mission is understand the stripping of the atmosphere by the solar wind, the processes by which the atmosphere is lost to space. Now, ideally, NASA would have funded us 4 billion years ago to do this, and would have had a global monitoring system in place for the last 4 billion years. They weren't far-sighted enough to do that, so we've got to play catch-up today. We're going to go and look at what's happening today and figure out how that tells us about what happened 4 billion years ago. So when we set out to propose the MAVEN mission, we proposed 3 basic questions, and these are what we want to address. What is the current state of the upper atmosphere? The composition, the temperature, the structure, the atmospheric motions, the dynamics, and what processes control it. The upper atmosphere is the conduit between the bottom of the atmosphere and space. Gases have to pass through the upper atmosphere, and since that's where the escape takes place from, that's the valve, if you will, that the gas has to leak through. That's where we want to look. What is the escape rate today? And what processes control it? If we understand how escape occurs today, we can understand how it occurred 4 billion years ago when the processes were the same, but the energetic drivers, the input from the sun, was different. And then using that, what's the total loss to space then through time? So this is a cartoon showing this. This is a cartoon of Mars showing all the different processes that we think can go on and lead to escape. And these are the things we need to measure. These are the things we want to understand. And we have instruments that are going to measure the energy input from the sun, since that's what drives the escape. It's going to measure the properties of the solar wind, the properties of the ultraviolet energy that can trigger chemical reactions, and major solar energetic particles that come out of storms on the sun that may trigger escape, may drive major escape. So we're going to measure the solar input. In the red here, we're going to measure plasma processes. Sunlight knocks an electron off of an atom and it becomes an ion. So we're going to measure the ion properties and the electron properties. And then the things in blue are the neutral processes. We're going to measure those. We have instruments designed to measure each of those three types of processes. I'm not going to go through them, but I've listed them all here. We don't really have, what is that, about 15 instruments. You'll see some of them do double duty, having the ability to measure solar wind properties and electron properties or ion properties. We've tried to pick instruments that would give us the best overall picture of the upper atmosphere. We have 8 instruments that we've selected to build to put onto this spacecraft. And if I really wanted to bore you, I would go through each one of them and tell you exactly how it works. I'm not going to do that. What I am going to do is tell you a little bit about how we selected them. When we sat down to design this mission, it's as close as I can imagine possible to sitting down with a clean sheet of paper and saying, what is it we want to measure? What is it we want to learn? What do we have to measure? How do we measure it? And then, is there one out there? We came very close to doing that, but you can't do it in a vacuum because you know what's out there. I talked to colleagues at University of California at Berkeley on the very first day that we thought about doing this, that we thought seriously about it. And when we agreed to collaborate, we thought, you know, we all understand the processes. Here are the instruments that make sense. And out of these 8 instruments, 2 of them are going to be built here at University of Colorado. 4 of them, that's this one and this one. This one is actually split between here and Berkeley, but the way I'm counting, the bulk of it is going to be built here. Caroline, don't contradict me because I'm really adding in bits and pieces of multiple instruments to get an average of 1. So we've got 2 instruments being built here. 4 of them, the 4 on this top row here, are being built at University of California, Berkeley Space Sciences Laboratory. It's a laboratory very similar to this one, about the same size, about the same number of scientists. They also do things that we do here, building instruments, doing science analysis, operating spacecraft. They do it in slightly different science areas most of the time. So these 4 are going to be built there. You'll notice that these 2 look identical. It's actually the same photograph, and the reason is, we cheat every now and then. The reason is that they're very similar instruments in their design, and this one measures the electrons, this one measures the ions. And if you think about it, if you know anything about electrons and ions, all you do is you charge the instrument positive one way, negative the other way to do it. So you can do it with very similar instruments. Then 2 of the instruments are going to be built at NASA's Goddard Space Flight Center, the mass spectrometer and a magnetometer. All of these instruments have tremendous heritage. The magnetometer has flown more than 50 times in space. Each one has flown, if not in its current incarnation for MAVEN, in one very much like it. So we have every confidence that these instruments can be built on schedule, on budget, and working properly. And one of the things I've learned in the last 5 years is the key operatives are on schedule, on budget, and working. You know, when I met, after we were selected with MAVEN, I met with the Associate Administrator of Space Science just for a courtesy meeting because I talked with them a lot, but we had a chance to catch up after we were selected. We talked about everything under the sun, the politics at NASA, the politics at Goddard Space Flight Center where he'd recently been director. And then on the way out the door, we finally talked about MAVEN. He grabbed me by the arm and shook his finger and said, just don't overrun your costs. We have a science team that is developed in order to work with these instruments. You'll see we've organized it by instrument. And again, I'm not going to go through them. But most importantly, we also have a group of interdisciplinary scientists, people whose interest is beyond just one of the instruments. We want to look at how it all plays together. The major science that comes out of this is not going to come from one instrument probably, but it's going to come from the analysis that has the results of all of the instruments embedded in it. And it's these folks who are going to do that analysis. So I expect they're the ones who are going to make the, allow us to reach the key conclusions. I threw this one in. It's the management structure for MAVEN. partly because I've learned that you can't give a talk about a mission without showing the org chart, organization chart. But really what I wanted to do here was to explain that this is what you would call big science. It's not two guys tinkering in a lab trying to figure out how to do something. The success or failure of MAVEN is going to depend on whether we have the right management structure. Because we're going to have, at a peak, I think, about 600 people, 600 full-time equivalent people, so maybe twice that if you count noses, working on this project. And it's impossible for anyone to know what anyone else is doing. You might know what the guy working next to you is doing on it, but with a project that is spread from coast to coast, Goddard Space Flight Center is outside of Washington, D.C. Berkeley is on the left coast, left in two different meanings. Colorado is on the Rocky Mountain coast. It's almost impossible to know what everybody is doing, and you have to have a management structure that works, where all the information goes up through mid-level managers to the project manager, who reports to me as the principal investigator on this. You know, I'm not sure what it says about me, but 30 years ago, when I was just getting started as a junior scientist, when the wiring diagram showed up, I turned off. I thought, what is the point of showing this? You guys, I'm sure, aren't interested. It's important to me to show it, but you don't want to hear about this. Today, I understand the most important thing you can look at is the organization chart, because this tells you whether it's going to work or not. Okay, let me tell you about the mission itself. I've told you about the science rationale. I've told you about the measurements we want to make and the instruments that are going to make it. But the instruments don't get there. The spacecraft gets there. And in a minute, I'll tell you about the spacecraft. We launched on November 18, 2013. And if you're doing the math, 2 weeks ago was 4 years from launch. So we have 4 years to make this happen. If we missed the launch window, this is the opening day of the launch window. It lasts for 3 weeks. If we miss it, we wait 2 years and change. The Mars Science Laboratory, if you're familiar with it, out of JPL, missed their launch window. They had technical problems they couldn't overcome in time. They slipped 26 months, and the cost of that slip is $400 million. That cost, their overrun is the size of our mission. Our mission is $485 million. It's either 485 million or 600, depending on how you count. How many of you guys read NASA Watch? Anybody? Okay, I'll talk to the three of you for 1 minute. You read that, and he makes a big deal out of the fact that you can't get a straight answer on how much a mission costs, because there are so many things that go into it, and whether you include it or not, you can get almost any number you want. And it's nobody trying to fool anybody or trying to cheat or hide something. It's the fact that you tell me what the ground rules are to calculate the cost, I'll tell you the cost. So we're looking at about $500 million. If we slip for 2 years, I don't even want to think about it. I guarantee you we're not going to. We'll be working 24-hour days if we have to get to launch, and if that doesn't work, we'll start working nights on top of that. We launched on November 18, 2013. We're compatible with either an Atlas V or a Delta IV. These are what's called EELV, which stands for Extremely Expensive Launch Vehicle. I've forgotten what it really stands for, but it's a category of launch vehicle. Once we launch, it takes 10 months to get to Mars. We go into an orbit around the sun, and when we get to the farthest point on that orbit, Mars had better be there because we're going to go into orbit around it. We time the launch so that Mars and the spacecraft get to the same point at the same time. I'm sorry, they get to points about 4,000 kilometers apart at the same time. Mars Climate Orbiter demonstrated that if you get to the same point at the same time, it's not a good outcome. Orbit insertion is 10 months after launch. Yeah, that's right. September 16, 2014. this picture is not to scale. I'll show you a picture of the spacecraft in a minute. We go into orbit with a single rocket motor burn about a half an hour long, and that puts us into an elliptical orbit. We're going to do our science from an elliptical orbit. This one is to scale. Mars in the middle, that's the red one. At our closest point, we're about 150 kilometers above the surface. At our farthest point, we're a little more than 6,000 kilometers above the surface. Since we're studying the upper atmosphere, this lets us pass through the upper atmosphere, going in and coming out every orbit. We're going to make measurements for 1 Earth year. In 1 year of time, we're going to see enough solar storm events, enough variability of the sun, enough opportunities to sample the atmosphere that we can address the questions we set out to answer. That doesn't mean we're going to shut off after a year, because there are some really good science questions that we'd like to answer that take longer than that to address. But our primary mission will be 1 year, and then we'll go into an extended mission. We have enough fuel to last in orbit for about 3.5 years. And the fuel just keeps the orbit trimmed so we're at the right altitudes, keeps us oriented properly. Once we run out of fuel, the mission really is over. It's not like some of these missions you see that last for 10 or more years. In the orbit we're in, we don't have the fuel. This is an artist's rendition of the spacecraft. It's going to be built by Lockheed Martin, which is located the other side of Denver down in Waterton Canyon. They have more experience with planetary spacecraft than any other spacecraft provider, and I'm just thrilled that they agreed to partner with us on this. For scale, we're looking here head on at it. The basic bus is this square, and it's a little bit deeper than it is wide. For scale, this is the high gain antenna, and that's 2 meters across. So the high gain antenna is about this high, well, the bus is about this by that, maybe as deep as from there to there. The wings go out about 12 feet or so on either side. These are the solar panels, and I'll show you a sideways view. You can see why they don't look like they go out straight. It's because they don't go out straight. The components of the spacecraft are all based pretty heavily on the Mars Reconnaissance Orbiter spacecraft that they built that's currently orbiting Mars. We're in the design phase, so we're considering design options. We're looking at changing components to make it look more like the Juno spacecraft, which is a more recent one they're building right now. And if we can get more modern components, if it turns out to be cheaper, we'll do that. You can see the instruments mounted on here. We've got a bit of a problem because some of the instruments that I described, the things we want to measure, are relative to the sun. So some of them want to point at the sun or be oriented relative to the sun, but some of them want to point at the planet. So you've got something pointed at the sun, something pointed at the planet. We decided to point the whole spacecraft at the sun, so we have the solar arrays illuminated, but then these instruments have to move and rotate. So they're at the end of a little boom here, a little longer than a meter, and it's a 2-axis gimbal platform with 3 of the instruments mounted on it, so it can rotate through all angles and look wherever we want to point it. We have another instrument mounted off the back end on this short boom, and then we have one instrument mounted at the far ends of the 2 rabbit ears. I have to be careful. How many of you guys understand the concept of rabbit ears? Everybody over 40 knows what that is. For you younger people, that's what used to sit on top of a TV, this V-shaped antenna going off in 2 directions. That's what that reminds me of. And then a couple more instruments mounted around the corners of the deck. Oh, and then the magnetometers, they want to get as far away as they can from the magnetic field of the spacecraft. So we've pushed them out to the end of the solar panels and then half a meter past that. We're not sure that's far enough. We may consider moving that out a little further, but that's one of the trade studies we're looking at during the current phase, the design phase. This shows it from the side. a sketch of it. You can see the solar panels here, where it comes out straight and then is swept back. We put in that gull wing shape because when we're at the bottom of the orbit, closest to the planet, we feel the drag from the upper atmosphere, even though it's really tenuous, and we want to make sure we're aerodynamically stable. It's like a shuttlecock. We want to make sure that if we hit the atmosphere at the wrong angle, we don't start tumbling. So by sweeping it back, it pushes the center of pressure back further relative to the center of mass. And if we go in at an off angle, it'll just right itself and point in the proper direction. So during the orbit, this is now a diagram showing the altitude as a function of time throughout part of the orbit. We want to sample the entire upper atmosphere. And we want to get from this altitude called the exobase. That's the altitude that the atoms actually escape from. It more than anything else defines the top of the atmosphere. Every orbit, we pass through the entire atmosphere, the entire upper atmosphere, get to below that exiting altitude, and then go back out. We want to sample deeper, though. We want to get down to the bulk atmosphere. The altitude where everything is well mixed, where it's homogeneous, and that's called, the top of that is called the homopause, where it stops being homogeneous. We're going to have campaigns where we lower the altitude of the lowest part of the orbit in order to get down to the homopause. We're calling these deep dip campaigns. We can't fly every orbit at that altitude because some of the instruments would be harmed, and because the drag is high enough, we would pretty quickly, the orbit would decay and we'd crash into the planet. So we're going to do every orbit down to 150 kilometers altitude, and then 5 times during the mission we're going to have campaigns that take us down to 125 kilometers. That lets us sample the entire upper atmosphere. Over the course of the orbit, over the course of the mission, the orbit doesn't stay fixed relative to the planet. The gravitational tug from the planet causes it to precess. So it precesses in 2 ways. In latitude, so that lowest part of the orbit sweeps through all latitudes, and then the whole plane of the orbit rotates around the planet, like that. You can sort of see this here. This is Mars. The sun is way off to the right. The different regions of interaction with the solar wind. And these white ovals mark the history of the orbit over the mission. So we have sometimes when we're upstream and we sample the solar wind before it gets to the planet. Sometimes when we're in the wake and we sample a very quiet part of the atmosphere. And over the course of the mission, we sample all the different regions. And I think I'll leave it at that for right now. So where in the solar cycle are we going to be? You guys know, I'm sure, that the sun goes through an 11-year cycle of activity. We just got out of solar minimum, and we're headed up towards solar maximum. MAVEN will get there. This is where we are today. This is a prediction. MAVEN will get there when we're going from solar minimum back down toward, from maximum back down toward minimum. That's a time when the sun is very active in its storms, and when the solar ultraviolet light is changing dramatically. That's the ideal time for us to measure. That's another reason we don't want to miss our launch window. If we get delayed 2 years, if you just pace off 2 years, that puts us getting to Mars at solar minimum, which is the least interesting time to go measure it. We want to be measuring it right in here. So we're going to make these measurements. How do we put it together? How do we extrapolate backwards in time for 4 billion years? Well, the first way is we measure these isotope ratios, things like the ratio of deuterium to hydrogen. And that directly lets us determine how much gas has been lost, integrated over the whole planet, integrated over time. The second way is we're going to understand all of the processes that are occurring today. And we know what the history of the solar wind has been. We know what the history of the solar ultraviolet light has been from studying other stars. And we can develop the models that explain what happens today, and then see how they operated, see how they would operate under conditions from 4 billion years ago. And then the third way is we're actually going to be measuring when the solar ultraviolet is changing, and we can use that to extrapolate directly. So I think, even though it's sort of weird to make measurements for 1 year and talk about what happened 4 billion years ago, that's what we're going to be doing. And I think it's pretty credible. We're going to do the mission operations at Lockheed Martin. This is a picture of their mission support area where they do the operations. They're operating, I've forgotten now, I think 6 spacecraft today, including 2 in orbit around Mars. They'll operate our spacecraft. We're going to be doing the Science Operations Center, the Science Operations here at LASP. And this is a picture of the Operations Center right outside there. And both of these pictures are a little bit fake in the sense that most of the time there's really nobody there. Things are pretty automated. We're only going to have 2 contacts per week with the spacecraft, so most of the time nobody's going to be sitting at the console monitoring it. But people are going to be working hard to make sure that it's doing what it should be doing, and they're going to be analyzing that data throughout the week. The Science Operations Center will be here, and we'll be coordinating among all the instruments to make sure we're doing the right measurements, that we've got a coordinated set of measurements that play well together. We're going to have a vigorous education and outreach program. We're using things like Twitter, Flickr, YouTube. I have no idea what these things mean, but hopefully some of you guys will. We're going to figure out how to get this out to the public. You know, as simple as having events like being able to participate in events like tonight's and talk about what we're doing. Hopefully in 5 years, when we start to get data back, Aaron will invite me to come and tell you what it all means. And hopefully I will have an answer.
Don't forget to tell them that we already have our Facebook.
That would be my slide after this one.
Oh.
Yeah, we've already created a Facebook page where you can get up-to-date information on what we're doing and find out everything you want to know. And in just a minute, I'll tell you how to find it. Our schedule, where are we? I've actually been doing this for 5 years, and we are 4 years from launch. What that means is I'm over halfway there. It just happens that 99.9% of the money is still to be spent. We wrote a proposal. NASA put out a call for people that wanted to fly missions. 20 different teams responded with proposals for full missions, and ours was one of them. My estimate is each proposal costs somebody $2 or $3 million. So it's not a trivial effort. It's a lot of work by a lot of people putting their heart and soul into it to make it happen. They selected 2 of those missions for what they call a Phase A study, which is, here's a couple of $1 million, now go and do it in more detail, do it right. We did a Phase A study. We were all set for the site visit, which was part of the review of that. We had to turn in, the proposal was this thick. The result of the Phase A study was a document about this thick. And it gets reviewed by a team, including the team comes and spends a day grilling us to make sure, give us every chance to correct our mistakes. We were all set for the site visit, and the day before Thanksgiving, I got a call from one of the people at NASA headquarters. He goes, "Bruce, have you seen your email lately?" I go, "No." He says, "You might want to take a look at it. We've postponed the site visit." They discovered a conflict of interest on the review panel that they'd not discovered. In the end, they couldn't resolve it. They couldn't fix it. So they had to delay the mission 2 years. Since the launch in 2013 is a different opportunity than 2011, we had to redo our Phase A study. So that's why it says Phase A and what we called Phase A Prime. A duo. They gave us a mulligan in golfer terms. I got this call about the postponement the day before Thanksgiving, and on Sunday of Thanksgiving week, this would have been 2 years ago, 2 years and a week ago, we had 25 people flying to Denver to start the lead up to the site visit. So we were frantic, trying to get hold of everybody to tell them, don't come. And we left voicemails, emails. Well, everybody got the word except one guy. He had already left for Thanksgiving break, didn't check messages until he got into his hotel room in Denver. And the email we got from him was labeled, "Oh my God, what do I do?" He flew back home. He was from Goddard. The good news was when we actually did the site visit for real about a year later, he already knew the hotel. He knew how to find it. Selection, they had two teams competing. We won the selection as the lowest risk, highest science mission. So we're moving forward to flight. We had a year-long phase called risk reduction phase where we worked through a few of the riskiest issues. It culminated in a systems requirements review, which was our first major review. We're now headed toward our next major review, the preliminary design review next summer. We have about one major review a year. This is the year that the real money starts getting spent. We spent $6 million in the last year. In this year, we're going to spend 40. Next year, we're going to spend 140. This is what it costs to do a mission. This is where it all adds up to $500 million. We have our final review before building it just under 2 years. We have a 2-year phase of building the instruments, building the spacecraft, putting it through what's called ATLA, assembly, test, and launch operations, culminating in a launch campaign down at the Cape in Florida, where everybody's going to go and work 36-hour days trying to get ready for launch to make sure we meet that launch window. And then I've described the rest of this. Right now, our nominal end of project is in April 2016. If we get an extended mission, it will go on past that. I lied, I forgot I had these other 2 slides stuck in there before I get to that Facebook site. The theme, coming down to the wire here tonight, the theme of the Mars program for the past decade or 2 has been follow the water. Water is the key component of life, and water is the underlying theme or the overarching theme of everything we're doing. Was there ever life? What has the history of the climate been? How does water affect the geology? And can we use it to prepare for human exploration? The last 2 decades of missions, Mars Global Surveyor, Pathfinder, Odyssey, the Mars rovers, Mars Reconnaissance Orbiter, the European Mars Express, the Phoenix mission, the upcoming Mars Science Laboratory, all tried this follow the water approach from the perspective of the geology. They looked at the surface, either from orbit, looking at the surface, or on the ground, digging it up and looking at it. We're going to be looking at the atmosphere to follow the water. And it's, the way I look at it, it's the necessary other half of the story. It's the other side of the coin. If you follow NASA, you'll recognize this format of showing what the whole exploration program looks like. Is that launch already? We have 5 spacecraft operating on Mars today. Mars Express, Odyssey, and MRO in orbit. 2 Mars rovers on the ground. One of them has its foot stuck in the sand, can't move, but it's still operational. I still count Phoenix as operational, even though it died about a year ago, because they're still doing the first major analysis of the data. The Mars Science Laboratory launches in about 2 years, a little under 2 years, and then we go next in 2013. Everything beyond there is a blur. It's undergoing this replanning that seems to happen about every 2 years, and I can't tell you what's going to happen. The most likely scenario is instead of these orbiters, landers in 2016, there will be an orbiter, and then in 2018 a lander, possibly a sample return mission in the early 20s. So you guys who are actually in your early 20s may still be around to remember it when it happens in the early 20s. Some of us who are pushing for it will be retired by then. I think my retirement date, according to the Social Security Administration, is 2020. God, that doesn't seem so far away now. Bottom line is MAVEN is on track, and I'm not going to bore you with these bullet points, but I will point to our interim website. at lasp.colorado.edu/maven, and our almost brand new Facebook fan page. You can sign up and become a fan. The easiest way to find it is to go to Facebook and do a search on MAVEN Mars atmosphere, and it'll pop up. If you do search just on Mars, you get this TV show Laura Mars or something. If you do it on MAVEN, you get all the meanings of the word MAVEN.
There's
So
some band called MAVEN too.
they stole it from us.
Yeah.
They are not related to us. Now I can't tell you how thrilling it is to be involved in a project like this. To imagine that we're going to build something that is about twice the size of this middle desk, and we're going to put it on a rocket and send it to Mars. And it's going to get there and tell us things about the planet that we really want to know about. It's going to help us answer questions about habitability. It's not going to find life or search for evidence for life, but it provides the necessary context to understand how and why Mars could have had life. And all I can say is stay tuned. I can just promise you an exciting ride for the next 4 years, and then hopefully some exciting science coming out of it. So again, thank you for coming out on a cold Mars-like night.